Good afternoon. I'm honored to be here to present the work of Drs. Lac Nguyen and Paul Griffin. My name is Wesley Dyke. I'm a Senior Quantum Solutions Architect at QCI, and regretfully, Lac was not able to be here to present, so I'm here in her stead. As QCI is a publicly traded company, here's the obligatory slide on forward-looking statements. Non-convex optimization is incredibly difficult. In fact, it is NP hard, and that is the motivation for QCI to have created a special purpose optimization solver. There's many solvers and devices that exist for solving optimization problems, but we believe that entropy computing will be a leader amongst our peers. Optimization is a central part of use cases in quantum computing, and with our method, we have more robust implementation. We have a lower barrier to entry, more gentle learning curve, and potential to reach near-term advantage versus our competitors. There's the all-optical implementation of EQC. You see it here. The color-coded highlighted portions are the key takeaways. You see the mixer, encoder, mode projection, and entropy coupling and amplification, which together create many states of the target Hamiltonian and subsequently eliminate high loss states, which represent poor solutions to a problem. In EQC, we have a flexible encoding scheme. We target this continuous variables as our main encoding. It's a quasi-continuous encoding with the values of the solution encoded as photon numbers within a train of time bins. Here's the hybrid implementation of EQC, and this is a diagram that shows what's inside the system of Dirac-3. You see optical and electronic components in the dark and light colors on the screen here. And if you want to talk more about it, you can come see us at the QCI booth, and we'll fill you in a little bit more. But here's the interesting thing. Now, Dirac-3 is able to avoid or escape local minima in a highly non-convex function, and you see we've got Dirac-3 and gradient descent both progressing through samples, and at each step you'll see Dirac-3 escaping or avoiding local minima and reaching the ground state, whereas gradient descent always ends up in a local minima, given the starting position. And while gradient descent isn't the end-all of classical optimization methods, it's a good example of one of the issues with using a classical method to solve non-convex problems. Now here's some concrete facts about Dirac-3. We can encode integer and continuous variables, and this is new. We have up to nearly 10,000 variables that we can represent in the system, and it's all-to-all connectivity with up to fifth order of interaction. It uses the same or less power than a desktop workstation, operates at room temperature, and is packaged in a 5U enclosure. You can connect to it directly with Ethernet and talk with gRPC. Here's the path on how we will get to the all-optical implementation of EQC. It is a collaboration between our thin-film lithium niobate foundry and our researchers in our lab in Hoboken. Here's one of the components that is being built or being fabricated at our foundry. This is a micro-ring resonator. With components such as that micro-ring resonator, we will build circuits such as you see here, which will be the realization of reduction in scale of the size of our devices. And now I'll pass it over to Dr. Griffin.
Okay, thank you very much, Wesley. So, yes, my name is Paul Griffin. I'm from Singapore Management University. I've been working with QCI probably about a year or maybe over a year, and they've very, very kindly been enabling me to use their Dirac-3 machine. We've got a number of good results which are in publication process, but I'm going to talk to you today about one which has been published about a month ago, where we was working with a local bank in Singapore, who you can probably read at the bottom here, on credit card transaction fraud. So fraud, as you all know, is a very big issue. $43 billion estimated for this year. And one of the issues with transaction fraud is that there's very few fraudulent transactions, which is probably a good thing, but when you're doing machine learning, it's a problem. So less than 0.2% of frauds in the data set, and this means it's very difficult to do typical machine learning. Banks are still basically using rule-based systems which are transparent, they're easy to do the rules, they're cheap, but they're also brittle and easy to game. Once the fraudsters figure out what the rules are, then they can game them. There's various machine learning has been done over the last few years to kind of supplement this. Logistic regression, KAM, trees and boosting. But they all suffer from this problem with the imbalanced data set. There's not many frauds. And also limited high-dimensional interactions as well. So we thought, let's try this Dirac-3 processor and do some quantum machine learning. So yeah, data set we use, 284,000 transactions, low fraud rate, typical 70-30 train split. We did increase the number of fraudulent transactions synthetically for the training side, but not in the test side, and tested out of sample. The data set is available publicly if you want to have a go. So the way this works is that it's a kind of a hybrid classical quantum approach. If I have a laser pointer here. No. So it's a classical hybrid approach. So we start off by training a bunch of weak classifiers classically. Then we construct a landscape of those weak classifiers. Then comes in the Dirac-3 to do quantum optimization of those weak classifiers. And then we train up the model and then infer the model after that. So we tried a range of different weak classifiers. And we measured both the accuracy in terms of the frauds being detected, but also, kind of more importantly in this case, the frauds which are falsely identified. And the results come out quite nicely. So first of all, we got the AUC, ROC, which is the accuracy. So this is the frauds which have been correctly identified. Already the classical benchmark is up at 97%, but even so, we've still got a bit of a bump up to 98%, which is quite nice. But the key metric really which we're looking at and which the banks are actually interested in is what's called here the AUC PR, that's the precision recall, which classically was 74%, and we got this nice boost up to 81%. And what that means is that we have less false positives. So true positives are great. You pick up the fraud, then somebody goes and deals with it. The problem with the false positives is that somebody still has to go and look at the fraud, and then they're wasting their time. And also the customer experience can be damaged. If a fraud is detected, you may get your credit card stopped, and who here hasn't had their credit card stopped. Then they find out that it's not a fraud and they've wasted their time, they've had a bad customer experience. So going down from the benchmark of 21 false positives on the classical to 7 with the quantum is a big boost, and the bank is well, I can't speak for the bank, but I've heard discussions that they're looking to kind of productionize this as another kind of supplementary process around fraud detection and stopping the frauds, finding the right frauds and getting rid of the false frauds. So overall, the quantum enhanced boosting in fraud, the fraud detection quality, 90% relative improvement in the precision, a bit of a boost in the accuracy. Practical advantage, it was very easy to put this Dirac-3 into the process. So looking at possible productionization, larger streaming transaction data. This was on one data set, but we can stream it. The times to do the machine learning and inference is very quick. More calibration, alert, and online adaptive boosting. So we're still looking at how we can do this in a more dynamic way. So that's about it. And thanks to everyone. Thanks to QCI for giving you a machine. Any questions?
We would like to open the floor for questions from the audience. Is there any questions from our audience? ご質問のある方いらっしゃいます。
If you have any questions, please raise your hand, please. Over there. Hi, こちらでこのメリットがどこ
reason why it's performing better?
It's a very good question. And it's something we're kind of exploring with these other projects as well. I mean, there wasn't much sort of time to look at the exploration here, but what we're seeing with the Dirac-3 processor compared to classical optimizing in particular is that classical optimizers may give you kind of one good optimal, but with the Dirac-3 we're finding a lot of good solutions rather than the best one. And particularly in the finance world, that's gives you a more resilient, robust solution. So you may find the optimal solution with one data set one day, but in the next day, if the data set changes a little bit and then your optimal solution is completely wrong, it doesn't help. So what we're also finding with machine learning as well is that the models we build with the Dirac-3 optimizer are more resilient, moving from the test data, from the training data to the test data or evaluation data. It seems it's the solution, we get more solutions around the optimal point rather than just one point which is optimal for that data set. So it's kind of a maybe some more kind of stochastic optimal rather than a deterministic optimal.
Hello, thanks for the presentation. I was wondering, very similar to his questions earlier, so the quantum part is being used to optimize the weights for each of those weak classifiers, right?
Yeah.
So is it just the weights that are giving this better results, or the classifier themselves are improved?
So I mean, the weak classifiers are trained up classically,
Sure.
so I assume that they're kind of doing their job. So it's really the optimization of the weights of those classifiers in the boosting algorithm, which we're seeing giving the advantage.
So the benchmark used the same weak classifiers?
It used some of the weak classifiers. We used a lot more to actually try out different classifiers. The benchmark used one particular type of classifier.
Okay, thank you.
Okay, thanks.